So in this video, what I'd like to do is talk about the implications of assuming that some process happens at um, some constant rate. And when I say rate, I don't mean that it's constantly happening. What I'm interested in here is some event, for example, radioactive decay of a molecule or division of a bacterial cell. So I'm going to talk about the bacterial cell, even though what I'm going to describe is a terrible model in the details. So what I'm interested in knowing is how is the time required, or the time that we wait, the waiting time to see a division event, if for a given cell to split into two, how is that time distributed? And so I'm going to make the assume that if the event hasn't happened, at time t, then the probability of the event happening in the next delta t, or the next delta t, so the probability of the event happening in the next delta t is constant. In other words, if this is time, and let's say the mother cell divides here at t equals 0, and by this point in time right here, let's say 1.5 seconds or 1.5 minutes, if the cell still hasn't divided by that point, then in the next delta t, I have the exact same probability of seeing a division event as if I look 3 minutes later and ask the same question about the same delta t. So the probability here is equal to the probability of seeing a division event here, under the assumption given that I have not yet divided at the beginning of the interval. Okay, so this is the fundamental assumption that I want to make, and anytime I have this assumption being valid, I'm going to be able to say something about the distribution. In particular, we're going to see that we get an exponentially distributed time. Okay, so how do we get that? How do we see that? So the first step in doing that is thinking about how do we write down that probability for that interval delta t. So I'm going to use a function g of t. So now you can think, before I was saying for a fixed delta t, but now if we modify the size of that delta t, so we expand it out or we shrink it down, whichever one, we can see that the probability ought to change, because if the sort of instantaneous rate of the division event is something for a particular delta t, if I shrink the interval, you can be certain that it's going to be less, and if I increase that interval, it's going to grow. So this is some function g naught plus g1 times delta t plus g2, and now I'm writing it out as a Taylor series in delta t because, sorry, this should be dt's. So the reason I'm writing it out as a Taylor series in delta t is because I'm interested in knowing how this all behaves as I let delta t get small. And so delta t is going to be close to 0, and it seems reasonable that this should be a smooth function near delta t equals 0, so a Taylor series should work quite well. Okay, so I'm not going to go through this, but at the end we'll have gone through a method that can be replicated in 2 particular instances, and I'm just going to make the claim, one claim here, that if g0 is not equal to 0, then the model that we would get from the same calculation I'm about to do, then the event occurs immediately. Okay, and that's unrealistic for most situations. I mean, if I'm looking at radioactive decay and I can conclude that the event occurs immediately, then I never have any radioactive material. It just disappears right away. So that's probably not going to be realistic case, so we can ignore the g of 0 equals 0. So now let's suppose that g of 0 is equal to 0 and g of 1 is also equal to 0. In this case, then the event never occurs. This is with, a deterministic, in the deterministic limit of delta t going to 0, or the continuous limit of delta t going to 0. So that never occurs. So that's also something we're not interested in doing. So we're going to just assume that g of delta t is equal to g1 times dt, and because I don't want to carry subscripts around, and because g's look too much like p's and q's, I'm going to call this r times delta t. Okay, and I often use equals when I really mean approximate, and I'm kind of going ahead in my mind here, thinking I'm taking a limit as delta t goes to 0, so that's really approximately equal to r delta t in the limit. All right, so what are we going to do with this? Excuse me. So what we want to do is we want to use this sort of almost instantaneous notion of probability and try and build a distribution of times at which the event actually happens. So often when you're writing down a differential equation or trying to derive one, the goal is to try and relate some quantity of interest at time t plus delta t to that quantity at t. So I'm not going to go through why other things don't work, and it may not be entirely clear why I picked this one, but the obvious alternate, if you try it, you sort of go in circles trying to figure out how to get a good equation out of it, and this one works quite well, quite quickly. So if I define q of t to be the probability that the event occurs, sorry, not the event occurs, the event does not occur. The event does not occur before time t. Now I'd like to relate q of t plus delta t to q of t. So let's just get the timeline here again, and here's 0. So what I'm asking here is how does q of t plus delta t, which is, here's t plus delta t. So how does that relate to q of t? So the probability of not having divided all the way from 0 up to t plus delta t consists of two statements, and these two statements are independent statements. So the probability of not dividing all the way from 0 to t plus delta t can be broken down into the probability of not having divided anywhere up to t, and then an independent event, the probability of not dividing in some interval of length delta t. So q of t plus delta t is going to be equal to q of t, the probability of dividing through here. And then when we have two independent events and we have a constraint that they both happen, and we want to know we want to know the probability of both of them happening, we can take a product of the two, and that gives us here. Now, what is the probability that we're interested in here? The probability that the event does not occur in this interval, and the probability that the event does occur was r delta t, so we have to take 1 minus r delta t in this case, because we want the negation of that. Okay, so now what we want to do is rearrange this so we get a differential equation. And you can see that I get, if I multiply this out, I get q of t minus r, and I'm going to just rearrange the order a little bit to lead myself forward here to where I'm going, and I can rearrange the equation, bringing the q over to this side, and I get minus r q of t dt, and hopefully if you haven't seen it already, you're starting to see that I can divide by a delta t, and I'm getting a difference quotient here. I'm getting a pre-derivative fraction. And now, once I have this expression, I can take a limit on this side, and I get q prime of t. And on this side, nothing happens in the limit. There's no delta t in there, and I get r times q of t. So what this means is that the probability that the event has not occurred before time t, so if you go back to your differential equations memories, you can solve this in a number of ways. You can use separable techniques, so you can bring the q's over to one side and take antiderivatives on both sides. Or you can use an integrating factor, or you can just look at it and say, well, this is going to be an exponential function. Q naught e to the minus rt. Okay, so this is the probability that the event does not occur before time t. And so that Q naught, we could probably say something about what that Q naught is. And so let's think about what it means. Well, if we know at the beginning of the process right here, at 0, at t equals 0, the event has not occurred for sure, because that's when we started the process. So what that means is that the event has not occurred at 0 means that Q of 0 is equal to 1. The probability that the event has not occurred before time 0 is 1. And that means that when you plug that 0 into the previous equation, you get Q naught. So I know that now that Q of t is just a simple exponential with no coefficient in front of it. Okay, so this is the probability distribution. Oh, sorry. This is not really a distribution. This is just a probability of event not happening. So if we want the probability that the event does happen, we're really interested there in I'm going to call it capital P of t is going to be equal to 1 minus Q of t. So this is the probability that the event, so in more traditional probability terminology, we say if the random variable is capital T, we're interested in knowing the probability that t is less than or equal to some fixed little t of interest. That's usually how we write what we call a probability distribution. And so that's going to be given by 1 minus e to the minus rt. And that looks like, so it's 0 at 0, so there's 0 probability of the event having happened before time 0, and we get an accumulating probability of the event happening until it asymptotes to 1. So the interesting thing there is actually that any process that has this property that we started with over here will eventually happen. It's guaranteed to happen because this function that we just calculated goes to 1. And it goes there in a very simple exponential way. So what is the density of these events? So to get the density, unfortunately I have to write it, I'm compelled by habit to write it as small p of t is equal to p prime of t, so hopefully you can tell the difference between those. And that is going to be minus r e to the minus rt. Oh, sorry, there was a minus in front of the e to the minus rt, and the 1 disappears. So we're left with this guy, and that says that the probability density exponentially decays. And so, so this is, if I'm thinking about bacterial cell division, this is pretty clearly, claiming something funny, because bacteria early on, after they've divided, are totally incapable of reproducing. They haven't even replicated their chromosomes. So you would very rarely see an event, that early. And this is saying that the likelihood is highest. The events most often will occur early on and much rarer far down here. Distribution for bacterial division, for example, we'd expect to have some kind of a ramp up like this, and then it actually comes down. This is the waiting time density for division. This came out of a paper in 2007 in Science Reports by Van Heerden et al. And they found that it was quite close to a normal distribution with a mean of 75 minutes. and a standard deviation of about 20. And so clearly, bacteria do not have an exponentially distributed waiting time for division. Okay, so now the next question I'd like to address is what is the difference between these two distributions if I'm really interested in sort of a macroscopic phenomenon of many divisions? So in other words, each of these, so this is one option and this is the second option, if I calculate individual waiting times and I say, okay, I have one bacterial cell and it divides at some time, and that this time of division here is distributed either by density 1 or density 2. And then we have two bacteria cells, and then that one of those two will divide. But then the next division after is likely to come quickly because there were two that could do it, and now there's 4 that could divide from here on, and so it's even quicker the next time. And now there's 5 that could divide, so the next one is going to be even quicker, and so on. So if I generate a whole bunch of these waiting times from either 1 or from 2, and I build up a whole population of bacteria, how different do these two densities behave in terms of the whole population? Do we actually get exponential growth out of a population like this? Okay, so I'll stop there and we can discuss the question I just set up later.